All right. Hey again, guys. Just taught the rest of my classes today and just remembered that, hey, I didn't film another video. I meant to film a video, slides 11, 12, 13, maybe 14, something like that, to kind of talk about it. Because this is the big thing here. We're finally going to see the feasible region. That's right, the feasible region. So again, we're looking at this same graph here where we have number of adult masks, which is our A variable, number of child masks on our y-axis, which is our C variable. It says B there, it should be C. But anyways, X and Y is what Desmos accepts, so we'll look at all of them here. So the idea of this, of course, is that we've learned how to graph inequalities. We've talked about kind of all three. I did this one kind of quickly near the end of class, but anyways, the idea is we had three inequalities, three constraints, and we got to get the three to work together so that we can figure out what the best combination is that's allowed in all three, right? That satisfies all three of the constraints, okay? So let's go ahead and turn them on right now. So let's put all three graphs together. And it says, drag the graph around to investigate what the graph looks like. Where is the area that includes all possible solutions? That's right. Where is the area that includes all possible solutions? And what that is called, vocabulary word-wise, just say it out loud a few times. Say it out loud times. The feasible region. Feasible region, feasible region. Yes, vocabulary words. We want to know what we're talking about when we say feasible region in upcoming lessons. All right, so let's check it out here. Let's go ahead and turn it on here. This first constraint is this one here, right? We got the 18x plus 15y is less than or equal to 252. 252 is the amount of inches of fabric you have. Yes, 18 inches per, right, per adult mask. 15 inches per child mask. Remember that from earlier on in the lesson? Yeah, it's a lot of stuff here. A series of lessons, we got that there. So let's turn it on. Then the thing you graphed today, earlier in class, you graphed the elastic constraints. Let's check that out. Let's turn that on here. And whoa, kind of goes on one over here. Oh, weird. I'll zoom in. We'll zoom in. Okay, this doesn't go on each other perfectly. So maybe at this point you're kind of thinking what the difference is between these two graphs. They're pretty close, what the difference is. And finally, we have the child to adult ratio or adult constraint. So twice as many adult masks as there would be child's masks, right? We got to double the amount of child mask, and that has to be less than or equal to the amount of adult masks. So let's go ahead and turn that on. And boom, we get that here. Okay, that here. So here we can't shade to the origin or away from the origin because this freaking borderline goes through the origin, right? Through the origin right here. X is greater than or equal to 2y. That would be the same as y is less than or equal to 1/2 x. I think that we did that one in class. And then we get this constraint right there, this blue constraint. Okay, so this is the constraint we've been dealing with the least here. This is the category, the kind of combinations of adults and child masks you can have that satisfy the adult to child mask ratio constraint here. So for instance, what this inequality is telling me is that I can have 15 adult masks and 2 or 3 child's masks, and that's fine for satisfying that constraint. The problem is that's too much fabric and too much elastic as we put in here. So let's check it out here and let's see if we can isolate this. Let's see if we can figure out where the feasible region is, okay? So this is pretty tough here. Our feasible region, what about up here? What's the problem up here, okay? Are any points up here? So you gotta ask yourself for the feasible region, where are the points that satisfy all 3 of the constraints? Are they gonna be up here? Well, up here would satisfy the red constraint, which is the elastic constraint, satisfy the green constraint, right? Those are solutions here. But what about the adult to child mask constraint here? No, not included, not included. Okay, so this isn't part of our feasible region. What about down here? There it is. Down here would satisfy, so right here, it looks like where it's right here, would satisfy the blue graph, it would satisfy the red graph, and it would satisfy the green inequality graph right there. So here, this has got to be part of our feasible region. We'll maybe experience this a little bit more here, okay? So we have this here, and then looks like our graph, like, doesn't work to blue. It starts working for blue here. It works for green. It works for red. This is great down here. And then the question is where our feasible region ends. And look at this. It gets so close. Look at that. These freaking graphs get so close to one another. They're kind of almost overlapping, but not quite. Ooh, tricky. So our feasible region only goes up to right here, but that's okay actually because we just care about the lattice points in this one. So our feasible region basically goes up to these lattice points kind of thing here, but that's not how we graph it out. Okay, so let's maybe isolate this. Out here, technically, if we were allowed decimals in this problem, we couldn't have combinations right here because that would only satisfy the red constraint and the blue constraint, right here. But just inside that green constraint, here's where we're satisfying all of them. We got blue down below, right? And it goes up. Blue goes all the way up to right here. So blue's good. Green is good, right? Because everything below this line, it could be green right here. And everything below this line is red. So here, the green is sort of our defining constraints that sets up where the feasible region is. And you might be wondering, what the heck's going on, feasible region? This is how you do this, right? How you do this like by hand. You'd graph all three of the constraints by hand, and then you figure out where all three overlap. Includes all possible solutions. All possible solutions right here. The feasible region is where all three overlap. Okay, all inequalities. So all inequality graphs overlap. Okay, overlap here. So what I'm going to do is maybe take a screenshot. I'm going to move Mr. Fortin off of this one here. And maybe I can just show you where the feasible region is when I move it over to Notability, just so you can see how you would do this by hand. And let's see, because you might have a class, right, where it's just like, okay, graph these three inequalities, tell me where the feasible region is, and you got to be stuck there because you don't have a Chromebook to get going here. So the idea of this is up here, these points aren't going to work, okay? Right, these points up here, they do work for green, they do work for red, but they don't work for blue, right? Don't work for the blue inequality right here, okay? The problem with the points out here is that they don't work for green or the red constraint that we had here. So now we're talking colors, right? Colors. Remember, colors link up to like elastics. Elastic amount of fabric that you have and whatnot here, okay? And then we can't even do this little sliver that's right here, right there. We can't do that little sliver that's right there because that only works for red and blue. Doesn't work for green. So we need to, if I really zoom in here, I'm not going to zoom in here a lot because this feasible region is like very delicate. We can't, to get it exactly right at least. So we try to zoom in. Oops, since I want to print, I don't want to print. Yeah, I want to get my feasible region right here, right? So maybe I'll actually do a little note here. And like this, okay, so this right here, right, this little sliver right here doesn't work for green, right? We don't have enough elastic to make that many, right, that many out here. These are just decimals. There's like, in the context of the problem, it doesn't really matter between the amount of fabric you have and the amount of elastic you have. So let's just draw on the freaking feasible region. So let's do it right here. So let's do it right here. One thing to note, all these lines are solid, right? Are solid here. Because remember, our equations are true too. If we get them, the amount of fabric equaling exactly 252, that is a true solution to the inequality. If we get the amount of elastic equal to 198, that is true with our inequality. So the solutions on the actual border are part of the feasible region. Okay, so here I try to do this very carefully to show, like, you can barely see it. There's a little sliver outside of this that's red that wouldn't get included because green's not part of it. And there we go here. Boom. We shade stuff in, my friends. In class, we're shading these in, shading inside, shading in the half planes. Said half planes in class. Half planes that represent the solution region of each inequality. And then where all those half planes overlap, right? It's usually this defined region. And I stopped it at here, right? Because remember, the context of the problem is that the number of masks can't be negative. You can't have a negative amount of masks here. So let me zoom out, and I've found myself this is our feasible region right here, okay? So that's what we're talking about here, right here. And this is where my solution set is. Solution set is here. So there's lots of combinations of child and adult masks that he can use. He can do 10, 4. I think a lot of people said 10, 4 is maybe the best. He can't quite do 10, 5. He could do 9, 4. He could do 11, 3. This is the way we can quickly check out a bunch of combinations that work out. And maybe we can like mathematically figure out how he can make the most money, for instance, or what's the most amount of masks he can make. And it might be 10, 4 is good, 9, 4 is pretty good. I think 10, 4 is the best though. That's the most amount of masks he can make. 11, 3, he can do 11, 3. How about that? So there's 10, 4 and 11, 3. You can make 14 masks. Looks like the most here, right? Down here, we care about less, right? 3, 1. would be 3 adult masks and 1 child mask. Not very many, but he could do it. He could do it if he wants to. That's allowed because it's in the feasible region. Okay, feasible region, feasible region. That's the thing you learned today. Hopefully this video is helpful. Let's see if there's anything else that maybe I should talk about to help you out. Let's see here. Where's the area that includes all possible? Oh yeah, use the sketch tool to get the feasible region. So let's do this here. Boom, boom. And here you got to be careful to get it so it doesn't go out on the outside here. There's our feasible region. So this is what I'll be checking, guys. I'll be checking to make sure you shaded in this feasible region. Okay, and then you should be describing this. Okay, describing this. I gotta go. I gotta pick up my daughter, so I'm not gonna put it into words for you here. But what I would say is the region of common overlap amongst the 3 solution regions of the 3 inequalities. Something like that, okay? Something like that. Where they all overlap, that's fine too. Okay, so let's check it out here. Today's goals were this: graph all of our inequalities in one graph. Yeah, hopefully you know how to graph all these 3 things. I think we did an okay job kind of talking about that. Can't be perfect. And then this is a typo. Remember, this should be less than or equal to 198. Identify the region with all possible solutions. Hey, that's the goal of linear programming is we have these different constraints. Where can we find the common solutions for those 3? That's called the feasible region. Hopefully you know what that is now. And finally, graphing an equation of a line from standard form. The really easy way to do it, plug in 0 for y. You can just divide to figure out what your x-intercept is. Plug in 0 for x, you can just divide to figure out what your y-intercept is. And there you have it. You have an easy way to graph lines now. That's not y equals mx plus b. Because once you have the intercepts, remember, you just draw the freaking line in, draw the border line in, you're good to go. Or if it's an equation, right? If it's not an inequalities equation, you can draw the line in, and then, hey, you've got your equation graphed. Hopefully this is helpful. I will email me if you have any questions, write this reflection. I will see you guys on Friday. Got to revise potentially some old classwork tomorrow as part of your classwork, and then you have another homework problem set from the textbook for Thursday homework. Anyways, Friday, more graphing and feasible reason stuff. Bye.